Alright, so today I'm going to be explaining another interesting article about graph representation. So the title of this paper is GwAC, GNNs with asynchronous communication. So this paper in conference on graph in 2023. Most graphs have most message pathing methods that we know are synchronous, but this is one of the these are very brave authors that said that no, if we look at the asynchronous communication, then we will have some interesting properties. By the way, if you look at your brain, everything is asynchronous. There is nothing synchronous. There is no clock. And this paper studies the relation between graph neural networks and distributed computing models to propose a new framework for learning in graphs. Current graph neural networks are closely related to synchronous. This is a traditional approach to graph neural networks. And nodes operate in rounds and at the same time receive aggregated neighborhood information. It looks very artificial, but our brain is totally different. So their framework in this paper is asynchronous, that every message is received individually and at potentially different times. We prove this framework must be at least as expressive as the existing synchronous framework. So we further analyze it theoretically and practically with regard to several GNN problems such as expressiveness beyond 1WL, underreaching, oversmoothing, and etc. So GwAC shows promising improvements for all problems. So, for example, one node says I'm H, then sends message. He says, I have an H neighbor. So you see how beautiful they have pictured their idea. Detection of an alcohol, for example, in this graph, we want to classify this graph to see if it is an alcohol graph or not. You see how expressive, interpretable it is. The C atom initially messages every neighbor. Then H neighbors reply. But the C atom discards the replies. The O atom reacts and searches for an edge in its neighborhood. If O receives a reply from an edge, the molecule is an alcohol. Very interesting. So we argue that synchronous communication is not always ideal. Aggregation may bury a single important message between many irrelevant messages. Such a message becomes the proverbial needle in a haystack for the receiving node to find. Forcing nodes to act the same number of times can become an issue when learning problem requires communication over long distances. So consider a line graph where we want to send a message from V1 to Vn. Every node needs to participate for n-1 synchronous round, while it only needs to forward a message once. Distributed computing knows an antipodal paradigm to the synchronous round-based model, asynchronous communication. So in this paradigm, every node reacts to individual messages at different times and a different number of times than other nodes. So they introduced this GwAC that has these 4 contributions. Nodes follow a synchronous communication model. and they react to individual messages at different time, and act a different number of times. So they deal with underreaching, over-squashing, these well-known fundamental problems of graph neural networks. So let's recap what is GNN. So algorithm 1 is the synchronous GNN that everybody knows. About aggregation and update, everybody knows. But algorithm 2 is an asynchronous. And we will go through this. So synchronous GNNs are parameterized by 3 functions. Message is a learnable function to apply. Update learns how to combine the neighborhood messages to update the node embedding. And the gate, this function is optional and not used in every architecture. Nodes can decide that certain information is irrelevant to them. This is my favorite gate, my favorite, because it's very bio-inspired, very much. So nodes can decide that certain information is irrelevant to them, or they can elect to stop participating altogether. We want to highlight 2 characteristics. Every node acts in parallel, and nodes only receive an aggregation version of neighbor messages. These aggregations are usually permutation invariant. So, what is the definition of simulation? Let S be a synchronous message passing with L layers and A an asynchronous GNN. We say that A simulates S. It means that asynchronous message passing simulates a synchronous message passing if for all input graphs and all input features A computes node embedding for each layer and node V in G that S computes. So we will now demonstrate how to construct this asynchronous message passing. So we will construct this and show that for a graph we can compute, for example, for graph isomorphism network, we can aggregate messages, then we update it. We create A to follow the ideas from distributed computing. You know, this reference, Auerbach presented the alpha synchronizer, which allows asynchronous models to simulate asynchronous ones. The key notion is that of safe nodes. A node is safe if for one round after it receives a message from every neighbor, and a node transfers to the next round if it and all its neighbors are safe. We will use a similar notion and show that we can realize it with little overhead in GNNs. If the GIN we want to simulate has L layers and an embedding size of D, we create A to have embedding of size 2D plus 4. It's a linear overhead. The embeddings can are tuples with the following meaning: S the actual current embedding, A an accumulator for neighborhood messages, W the number of missing pulses, U the number of unsafe nodes, I if the node never acted so far, and L the number of layers left to simulate. So messages are tuples. There are no operation, origin, pulse, acknowledge, M, where the last of 4 are bits 1 hot encoding of message type. They're just message type. Origin used for first message to start execution. Pulse messages are only sent by safe nodes to transmit the next round's information. The remaining messages are necessary to synchronize the nodes. So this paper is so exciting. Acknowledge the receipt of the neighborhood messages, and no operation messages contain no information. Gate will ignore those. So you see this table 1 that you have different conditions. If acknowledge is 1, if pulse is 1, and then you get different messages. You can have different UIL. When node V emits its ICE pulse, it must have already received, this is a lemma, received I-D plus 1 pulse or origin messages. So this paper is very interesting because it is very unique. Very few papers. Another paper is why GNNs go hog wild, something like this. It's asynchronous as well. But these asynchronous methods are very much bio-inspired. And they can be much more scalable than what we do in current generation of graph neural networks. You see the graph classification accuracy of the proposed asynchronous one is almost the same. I mean, it captures and also slight improvement of, for example, graph isomorphism, graph attention, graph convolution, and graph sage. Not huge improvement, slight improvement. Again, these we have slight improvement. Sometimes we have bad cases. For this data set, the traditional approaches, we should see why they are better than this one. What kind of distribution this data set has that results in this kind of weird results. So about protein, they have almost the same. So it can capture the traditional things, the traditional achievements that we have. It can capture it. The asynchronous network here, they can capture these synchronous methods. And they have an algorithm, GNNs, in the asynchronous model, that they have random message delays. Again, another article is written by Bernstein in Oxford about that. They use kind of delay concept for far-reaching nodes and over-squashing and over-smoothing problem. Similar idea, but still they didn't use asynchronous stuff. So this paper is very interesting.